All right, so guys, calm down. So chapter 14, we'll do the solutions part before spring breaks. Our goal to finish that, then we'll save the other half for afterwards. You've probably talked about solutions at least a little bit in 8th grade maybe, or you should know what a solution is. You've all had some experience with either salty water or sugar water. So you've experienced something dissolved in water. Most of the topics in this chapter for us will involve something being dissolved in water. Okay? And that's not always the case for solutions. And that's really just a small sample of solutions, but for the high school level, something dissolved in water is the main thing we look at. Before we look at that, there are three kind of major types of mixtures we'll talk about to start with. You might have mentioned these in the 8th grade, maybe not. Solutions, suspensions, and colloids. So we'll kind of mention what those three are and talk about them. Then we'll focus on solutions for the rest of the chapter. So we say that solutions are homogeneous. So by homogeneous, what do we mean by that?
The same.
Yeah, the same. So when you look at it, if you look at a solution of salt water, do you see two different things? Do you see the salt and the water separately? No, you just see the solution. Okay. So y'all know what that word means, so you can leave that blank. But in a solution, once something is dissolved, the particles are very small or large? They're very small. Okay. So you take large crystals of salt, sodium chloride, and dissolve it in water. The particles, once they're dissolved, are very small because we can't see them, right? You can see the grains of table salt, but can you see dissolved salt in water? No. Okay, so two words that we use quite a bit, solute and solvent. So think about the sodium chloride and water example. You may know which one the solute is. The sodium chloride, okay. So the solute is the substance being dissolved. Then the solvent is the substance doing the dissolving. If you want to just make this note to keep it straight in your head, the solute is typically a solid. The solvent is typically a liquid. In most of our examples, the solid solute is dissolved by the liquid solvent. But it does point out in the next bullet that does not have to be the case. It's not always true. But for most of our examples, it is. So if you want to write that to keep it straight in your mind, you can. So kind of how we define solutions is they cannot be separated by filtration. So if you think about sodium chloride in water, can I separate the salt from the water?
No.
But can it be done? Yes, you can separate the salt from the water by different processes. But can you take a coffee filter and filter out the salt? No. So we can't simply filter out the solid. And they also do not separate by settling. Okay? So by settling, I mean, think about a snow globe. When you shake them up, you have the little pieces of snow or glitter, whatever it is, and they float around in the solution, right? But if you leave it sitting there for a while, what do the little particles do? They settle out. Okay? So if I have a cup of salt water, will the pieces settle out? No, it's not going to settle. They're all mixed together in a homogeneous way. They're all evenly mixed. Okay? One kind of exception to what we talked about with the solute not being solid and the solvent not being a liquid are alloys. So alloys are considered to be solutions by definition, but what are alloys? They're mixtures of metals. Okay? So due to their properties, they are considered to be solutions. Is that a liquid dissolved in a solid in that case? No. Okay, but it is a solution. So what is an alloy? What's an example of one? Steel, or brass, or bronze. Okay, think about brass. If you look at a piece of brass metal, can you see the different types of metals separately? No, they're all mixed together in a homogeneous way. Okay, so we can't see the difference, but they're made up of two different metals. Okay, so that's the common example of us having something that's a solution that's not really a metal dissolved in, not a solid dissolved in liquid. Yeah. Yeah, you can think about it like that. The state of matter doesn't really matter so much, it's how the final product is. Because you could have a liquid alloy or you could solidify it. So the last two words I think you all know, hopefully, we did double replacement reactions. If something is soluble, it is capable of being dissolved. Okay? If it's not soluble or insoluble, it is not capable of being dissolved. So with double replacement reactions, we thought about solubility as kind of like a binary thing. It either is or it isn't. So we'll talk about in the class today how even things that are soluble, they're only soluble to a certain extent. So is sodium chloride soluble in water? Can I dissolve it in water? Yeah. But can I dissolve an infinite amount in a cup of water? No, there's limits. Okay. So for double replacement reactions, we assume we wouldn't reach that limit. We assume we wouldn't max the solution out. But today we'll kind of discuss that. So that's what we'll focus on the majority of the time. But just very quickly, we'll talk about suspensions and colloids. So suspensions are mixtures where the particles are the solute particles are very, very large in relation to the solvent. So the example here is muddy water. So if you take dirt and stir it up in water, will it make a mixture? Yeah. But then could you filter out the dirt again? Yeah. So suspensions can be filtered. And they'll also settle. So if you think about the snow globe deal, if you leave the snow globe sitting there, the glitter falls back down. You leave the muddy water sitting there, the dirt and mud falls back down to the bottom, and you get clear water at the top. Okay? So we won't deal with those really in this class, and we also won't deal with colloids. There's some stuff typed out there for you to look at if you want to. Colloids are kind of the halfway point between suspensions and solutions. The particles are kind of intermediate in size as compared to solutions and suspensions. The common example there is milk. Okay, so milk has a lot of particles in it. If you think about a solution of sodium chloride versus milk, do they look the same? No, one stops light from penetrating, the milk does. But can you see the milk particles floating around? No, so they're kind of halfway in between that. So don't worry so much about those. We're going to focus the rest of the chapter talking about solutions. So let's talk for a second about the solutes of this solution. So we said that in most cases, the solute was some solid that would dissolve in the solvent. So there's really two categories that we'll put solutes into. That is electrolytes and non-electrolytes. So what do you think an electrolyte does? Well, this is the same electrolyte that's in Gatorade, but let's think about why it's called an electrolyte first, then we'll come back to Gatorade. I heard electricity. It conducts electricity. Okay, so electrolytes conduct electricity. When dissolved in water. We'll come back to Gatorade in a minute. So if electrolytes conduct electricity when dissolved in water, what do you think non-electrolytes do? They do not conduct electricity. So we can pretty much put everything in one of these two categories. You either do conduct or you do not conduct. So what is electricity? Like if I plug something in the wall, what's coming out of the wall outlet?
Electrons?
Yeah, electrons. Okay. So electricity is just the flow of electrons. Okay. So what do we know about electrons? What do they have?
Negative charge or negative?
Yeah, negative charge. Okay. So electrons are negatively charged. So in order for something to conduct electrons or carry electrons, it has to be charged. Okay. So what's the chemistry word for something with a charge? Ions. Okay. So you can ask why some conduct and some don't. So ions must be present to conduct electricity. Same thing's true with the copper wires that electricity runs through. There are moving charged particles there. The electrons are free to move. So now we know that in order to conduct electricity when dissolved in water, you have to have a charge. So let's talk about how things obtain charges when dissolved in water. The first way by which something obtains a charge in water is called dissociation. So dissociation is when ionic compounds, we'll just say ionic compounds, break down in water. We'll say break apart. So break apart is not the best scientific phrase to use there, but it gets the point across, hopefully. So what does an ionic compound look like?
A metal.
Yeah, metal plus nonmetal, or ammonium plus nonmetal, something positive and something negative together, right? So if dissociation or ionic compounds breaking apart, we can say most ionic compounds dissociate. So sodium chloride, sodium sulfate, ammonium chloride, ammonium nitrate, those are all ionic compounds. So let's write down what this looks like. Is sodium chloride an example of an ionic compound? Yes. So if I have a chunk or a crystal of sodium chloride, what state of matter is it in? Solid. And if I add it to water, it's going to dissociate, so it's going to break apart. So what charge does sodium have in this situation?
Negative and
Positive.
Positive, what? 1, 2, 3? 1. Na plus 1. If it's dissolved in water, what state of matter, or what phase symbol does it get, rather? AQ. Plus Cl AQ. So it's important to note here, the diatomic rules do not apply when there is a charge. Okay? So it's okay to have Cl negative 1 by itself. It's not okay to have just Cl by itself. Okay, this is chloride with a charge. So don't try to say Cl2 negative 1 AQ. Okay? Those rules do not apply when it's dissolved in water with a charge. Is that your question?
Yeah.
When you're dissolving it, do you write what it's being dissolved in above the arrow?
Yeah, we could write plus H2 over here. If we did that, we got to write it over here to balance it. So it's pretty common to write it right there. But if you wanted to write plus water, you could. Any other questions about that? So, pretty straightforward. You have an ionic compound, you put in water, it dissociates, has charged particles. Okay? So, did this dissociation produce ions?
Yes.
Yes. So would this solution conduct electricity? Yes. So now, ionization is a process by which covalent compounds break down in water. So the rules for when this happens are kind of complicated, but for this class, we'll say that only acidic compounds ionize. Okay? So if I say acidic, that means it's an acid. So what does an acid look like? What does it start with? H. Okay. So is HCl an acidic covalent compound? Yeah. So will it ionize? Yeah. So ionize means it's going to make what? Ions. So the process is the same as dissociation. It still breaks apart. Okay. So HCl, H plus, AQ, plus Cl minus, AQ.
Greg, what was HCl on the left side of the equation?
It didn't tell you. Just whatever. It's a liquid here though. But so would hydrochloric acid conduct electricity in water?
Yes.
Yes. But this says only acidic covalent compounds ionize. So we can make a note. Most covalent compounds do not dissociate or ionize. So most covalent compounds do not ionize. So let's think about just glucose, C6H12O6. Is that covalent or ionic? CH and O. Carbon, hydrogen, and oxygen. Covalent. Okay. So if I just have C6H12O6 in the solid form, so I tell you that it's soluble, it will dissolve in water, but will it ionize? No. Is it an ionic compound or an acid? No, so it won't break apart. So it just does this. Becomes aqueous. So if I put a big sugar crystal in water, will the crystal break apart? Yeah. But will the individual molecules break their covalent bonds? No. Okay, so now let's look at this little simulation. I'm going to pause the video recording.
Franklin, remember to start the video back.
Yeah,
Start the video back, Mr. Franklin.
So if we said that when certain things are dissolved in water, they conduct electricity, does pure water conduct electricity?
I thought.
Yes.
No. So water does not conduct electricity. But have there been many times in your life when you've ever encountered pure water? No. So here I have a gallon of distilled water. Do you buy this and drink it at home? No, because it tastes bad. We aren't used to this. Who has a purchased bottle of water? Read your label. Read your ingredient label.
Magnesium sulfate,
So magnesium sulfate,
potassium chloride,
potassium chloride,
salt,
salt,
minerals added for
some minerals. So is it just pure water? No. So what you're used to drinking is not pure water. Some bottles have it listed out. Some just say minerals added for taste. Okay. So if you ever drink distilled water, it tastes nasty to you probably. You're not used to pure water. What we encounter from the tap, is it pure water? No, there are things dissolved in it. Okay. So I'm going to pause the video and show this little light bulb real quick. Alright, so the main takeaway from that is, does pure water conduct electricity? No. When ionic compounds dissolve in water, does it conduct electricity? Yes. Okay. Let's turn the page and let's talk about kind of the general rules for solubility. So when we talk about whether or not something's going to dissolve, the general rule that we use for if something can dissolve something else, we say that like, L-I-K-E, dissolves like. And what that means is nonpolar solvents dissolve nonpolar things. Polar solutes or polar solvents dissolve polar things. Does that make sense? Polar and polar go together, nonpolar and nonpolar go together. So what kind of solvent do I need to dissolve a polar solute? I need a polar solvent. So what's our most common example of a polar solvent? Water. So I can say polar solvents dissolve polar solutes. So then what would dissolve a nonpolar compound? Nonpolar solvent. If you take organic chemistry, you'll talk about nonpolar solvents quite a bit. That's where it matters more. And then polar solvents also dissolve ionic compounds. Okay. So those are the basic rules for whether or not it will dissolve. Two other words, you can mark out hydration, don't worry about that one. So skip hydration. Two words we use to describe whether or not liquids can mix are miscible and immiscible. Okay? So one of these means they can be mixed, one means they cannot be mixed. Which one do you think means they can be mixed? Miscible. Okay? So this means that liquids can be combined. So if the rule goes like dissolves like, if I want something to mix with a polar liquid, the other liquid needs to be what? Polar. Right? So in your kitchen, you have vinegar, acetic acid, that is a polar compound. Can you mix vinegar and water together? Will they combine? Yeah. Okay. So polar acetic acid will mix with polar water. So immiscible cannot be mixed. What do you have in your kitchen that's non-polar?
Oil.
So cooking oil, vegetable oil. Can you mix together cooking oil and water? No, because one is non-polar and one is polar. If you wanted to mix canola oil and like avocado oil, could you mix them together? Yeah, they're both non-polar. Okay. So two nonpolar can combine. Polar and nonpolar cannot combine. What?
Is avocado oil a thing?
Yeah.
Yeah.
You don't cook much, do you?
Not avocado oil.
You need to expand your horizons. Branch out a little.
I've never heard of avocado.
You have to be vegan to eat avocado oil.
I think avocado oil, I guess.
No, they didn't.
Vegetable oil.
Well, anyway, let's get back to this. So,
Anyway.
anyway, there are, guys, calm down, a couple of things to talk about in relation to solubility. Before we talk about the rules for the amount of something we can dissolve, there are a couple of factors that affect how much we can dissolve. Okay? So, if I wanted to dissolve more salt in that water, what are some things I could do to dissolve more of that salt?
Increase the amount of water.
So increase the amount of water, but I'm still dissolving the same amount of salt per volume of water. So without changing the volume of water, how could I dissolve more salt?
Like a smaller container? Volume. Yeah, volume. Like,
Okay, well we can say stirring is one factor. So stirring or motion. Okay, so if I just add salt, it won't dissolve. You got to agitate it. Think about making sweet tea. How do you? So you heat up the solution. So add heat. So we can add heat with an asterisk. That doesn't always increase it, but it typically does. Well, for now it does. And the last one, think about a giant salt crystal versus a handful of salt powder. What's going to increase, or what's going to dissolve the most quickly, or the best? The powder. So we can say change particle, or we just say particle size. So we'll look at those with a lab after spring break, but for listen just for now. So now we had two words to describe the solute. We said it's an electrolyte or not electrolyte. Now three words to describe a solution based on how much is dissolved. Saturated, unsaturated, and supersaturated. So let's start at the third one. A solution that contains more dissolved solute than should be allowed under those conditions. That's supersaturated. When do we make a supersaturated solution in this class? Right before winter break. What do we do? Yeah, we agree with the crystals. So with the crystals, I heated the solution up and it was hot in your cup so I could dissolve more of the solid. Then when it cooled back down, the solid had to go out of the solution and form a solid. And it formed a crystal on your pipe cleaner. Okay? So then a solution that contains less would be unsaturated. Then one that contains the maximum amount is what? Saturated. Then the last blank, what we're going to talk about now, the amount of substance that we can dissolve at that temperature, we call the solubility. So before we said solubility was a yes or no answer, right? It is or it isn't. Now we can talk about how much we can dissolve. Okay. So at the bottom of the page there's supposed to be a chart. It didn't print for some reason, so you can cross that out. I don't know what happened there. We'll go to the next page. On the next page, you have what we call a solubility chart or a solubility graph. So what are the units for the x-axis? Degree Celsius temperature. And the y-axis has units of solubility. So grams of salt I can dissolve in 100 grams of water. So except for cerium sulfate, which we'll discuss later, as I increase temperature, does solubility increase or decrease? It increases. Okay? But do they all increase uniformly? No. Do they all change equally? No, it varies. Okay? So using this chart for any given temperature, could you tell me how much I can dissolve per 100 grams of water? Yeah, per 100 milliliters of water. Then could you also tell me, let's say at 50 degrees Celsius, I dissolve 60 grams of potassium chloride. Okay? So there's the solubility line. Let's say I tell you that I somehow dissolved 60 grams. Have I dissolved as much as I'm able, less than I'm able, or more than I'm able to? More. So is it saturated, unsaturated, or supersaturated? Supersaturated, okay? So could you also tell me, if I only dissolved 10 grams, how many more grams I could dissolve? Yeah, okay. Do you have to know very much chemistry to read this graph? So where do you see charts that don't require knowledge? The ACT. So this is a very good ACT style question. Does the graph look complicated? Yes, but is it? No, there's a lot going on. Okay, so take the next 5 or 6 minutes and answer these 12 questions. Okay, you can work with your neighbor. I don't care. They should be pretty straightforward though.